For his master's degree, Jaroslav decided to create a sonic art piece to demonstrate his abilities and knowledge of a few of his passions in life. He settled on the idea of a musical chessboard, meaning that you compose while you play. In this documentary, we'll have a look at how everything works, how it was made, for a truly interesting look into the mind of the creator. So without further ado, here is Jaroslav's musical chessboard.
The main idea underpinning this project is, I'd say, the relationship between me and my grandfather, who taught me chess as a kid. And he was the one to introduce me to music as well. So I kind of wanted to join the two in some way. And I didn't really realize that at the time that I started working on the project. So I think it was something subconscious kind of telling me what to do. And once I kind of recognized that this might be the case, I thought it would be really fitting to use my grandfather's chess set for the piece. And so I did, yeah. This chessboard is a part of a musical installation, or like a sonic art piece. So it is used to basically just play chess, except all the chess moves are kind of converted to MIDI information and sent to the computer where they're further worked with, and they would generate sound live in real time as you play chess. So basically the chessboard would just compose music for you. Not just the board and the computer, obviously, but yeah, MIDI is basically a communication protocol which enables musical interfaces or musical instruments like synthesizers to communicate with each other. I think as a composer, it's a good idea to use other tools to kind of expand your composer's toolbox, and using a chessboard in musical composition opens up new possibilities for you as a composer that you would have never thought of. It's kind of difficult to describe it because there's so much going on. I think, if just to sum up some of the most interesting features, for example, if you perform castling, right? In chess, you could either like castle, castle short, like that, or you just go and castle long, which does really make a big difference in chess. So I thought it could make a big difference in music as well. So if you castle long, I was thinking, why not elongate all the melodies? So all the melodies that are assigned to white, they would go half time, they would be twice as long. If you castle short, then the opposite happens. So all the melodies go double time, it would be twice as fast. Same happens for black, although only the melodies triggered by white or black respectively get affected by this. It's also worth noting that the timbre of each melody triggers is dependent on the state and the position on the board at the time that that particular melody is triggered, and it stays like that for as long as that piece is on the square that triggers that particular melody. So let's just do like a really quick sequence. So I mean, you can see it all here. So let's start at basically like E4. So now the clock started. Let's respond. E5. We'll do nights. Whatever, something like that. And now I'll just respond like this. So basically, I'll lift the king, lift the rook, just put on castle now. Now it's black's turn, so you could go like there. And why not do long castle for the black to see just how it would change the melody. I just need a couple more moves in order to be able to do that. Let's go that. Doesn't really matter. So I'm finally able to long castle with the black. So just lift the king, lift the rook, put the king where it's supposed to be, place the rook. And now all the melodies triggered by white, they're in double time. However, all the melodies triggered by black, they're in half time. The chessboard is made out of 64 squares, right? So underneath every single square, there's a Hall sensor, which is a sensor that, kind of like transistor, would either allow the flow of electrons to go through or it would just block it. Except, unlike transistor, in order to kind of open up the flow, you wouldn't use electricity, but you would use magnetic fields. So that's why I put tiny little magnets underneath every single piece. So once you place the piece on the board, you would kind of close the circuit, which there's a microcontroller underneath that kind of sums up all the data from the board, and it would see whether there's a piece on that particular square, whatever square it is, or whether there's no piece at all. And it would send the information to the computer in the form of MIDI information. So it is really convenient to do this because now they can communicate together, because it's basically a musical language. That's kind of the first step, having the chess game converted to a stream of MIDI information. However, what you do with the MIDI is entirely a different thing. If I was simply to send a MIDI to computer, I could just trigger like synthesizers or percussion or samplers in the same way you would do with a just ordinary keyboard, except it'd be a chessboard. So in a way, you could do that, obviously, but I think you could do so much more with this as well. So that's why I just decided not to take the obvious route of just, playing notes or assigning notes to individual squares. I would have the computer figure out how many pieces are in each individual row or column on a chessboard, then how many pieces are in each individual quadrant on the board, and all sorts of things like that, which would give me a bunch of numbers basically that I could assign to musical variables. So, for example, the number of pieces, or actually the ratios of pieces in each individual quadrant, would determine the panning in the piece. So let's say if all pieces were just in this corner, the sound would be only coming from there. It wouldn't be going from all sorts of directions. It does so much. It's just like 50 things it does. It's just like, I'm really not sure how to structure it so it makes sense, because I don't even remember what all it does. I mean, if I just run through the chord here. It's like there's compression going on, it's reverb, it's the rhythm and the pitch sets, they're kind of given. However, the timbre and the kind of spectral information, that's all based... you know what? Let's talk about additive synthesis, because that's kind of important. So when you want to synthesize sound, one of the kind of crude approaches you could take is additive synthesis. So you would take a sine wave and you would generate the harmonics and kind of sum those sounds together. So you would choose how much of each individual harmonic you want in the resulting sound. So I was thinking, why not go for 32 harmonics? That's basically half of the chessboard. So it would be 32 harmonics for white, 32 harmonics for black. And I would go, let's, for example, determine the levels of each individual harmonic by the number of pieces in each individual column and row. And then I was thinking, that's only 16 because 8 plus 8. So I was kind of coming up with all sorts of geometrical shapes derived from the chessboard, like 2x4 kind of rectangles, which gives you 8 squares as well. All sorts of these informations. Though the issue that I ran into quite early on was that it was just too many calculations, way too many calculations for the computer to perform. So it was crashing, and I had to kind of cut down the amount of harmonics I wanted to include, because if I was going for 32 harmonics per each individual note, or at least each individual square, you get 64 squares, 32 harmonics. So that's basically 64 by, multiplied by 32 for each side. So multiplied by 2. It's just an awful amount of oscillators running at the same time, since oscillating at different frequencies. So there's no way to kind of make it easier, if you don't want to just use like samples or anything like that. So I just settled with 16 harmonics, and each time you play a move, the board triggers melody that's assigned to each individual square. It would pan it accordingly to the position on the board. It would determine which harmonics are present and which are not, and it would also determine the relative levels of harmonics in the resulting sound. One of the main inspirations for the project is basically the musical minimalism. So usually what minimalist composers would do is take like a fragment or a melody, or a couple of them actually, or it could be as many as you want, and they would kind of start stacking them on top of each other. So they would kind of complement themselves, but the melodies would be of different lengths or different articulations or something contrasting. It could be whatever you want, but they would add up in quite unexpected ways. And the more you have, the more complex the system becomes. So I was thinking, why not assign each square with its own melody? That would work quite well, but it doesn't have to. So I had to make some considerations in order to make it more predictable. And I kind of drew on my experience doing neo-baroque music. So I actually only composed 16 melodies for the first quadrant. And I was thinking, it's kind of a mirror, almost a mirror image of itself. If you just flip it like that, and then you just flip it like that, and flip it like that, and you have the whole chessboard. So I was thinking, why not do that with the whole bunch of these melodies? So I basically decided, because what you could kind of do is to take the quadrant 4x4 and flip it this way, and you can flip it again this way, and then you can flip it again this way. I was thinking, why not do that with the melodies? So you would have your melody here, or 16 of them actually, and you can play them in retrograde. That means like playing them backwards. So that's flipping this way. But then I was thinking I could do inversion as well, so where you invert the intervals. So if your melody is like third up, second up, I don't know, whatever, seventh down, you'd go third down, second down, seventh up. That's how you invert your melody. But it's the melody backwards as well. And then if you flip it once more, you still got your inverted melody, but now you're gonna do it backwards to, relative to this quadrant, relative to this one, it's gonna be in the same direction, except all the intervals are just different. So, doing it this way kind of ensured that you have a unique melody for each individual square, but there's still some sort of logic underpinning it all. They're kind of still relatives in a way, which should, in theory, help them work better together when you start stacking them on top of each other. It's kind of a common theme in Baroque music to actually do this in the fugues, when you're doing imitations, working with like melodic themes. You could have a theme, you can invert the intervals, you can have the theme backwards. You could do what's called augmentation of the theme, which means you make it twice as long, like every single note is gonna be twice as long, or you can do diminution of the melody as well. You make it shorter, so it's twice as fast. It's basically the half time and double time thing. So for me, this project was mostly about kind of merging all of my experience in music making to one. So it's got Baroque influence, it's got minimalism in it, it's got a bit of coding in it, it's got quite a lot of my childhood memories in it as well. I was actually using the actual chess pieces I learned chess with. So it's kind of a meeting point of all of these influences and ideas. It's got microtonal music in it as well. Because, quite early on in my composition practice, I started playing with the idea of field tonickeit, which is a term, kind of artificial term from one of the essays I was quite impressed by. I don't remember the author, unfortunately, but in historical music, Baroque, or even before Renaissance, and even before that, basically everything before modern music or 20th century music, there were quite a few schools of thoughts on how you tune your instruments. And because tuning an instrument is mathematically unsolvable issue, so there's been so many possible, not solutions, but more like workarounds, let's say, around these issues that arise from basically just the mathematical facts of musical tuning. And I really like the historical approach, where you would have more tones or more notes with the same name of a slightly different pitch. So you can have like C4 and it'd be like 5 different frequencies depending on the context. However, that's quite unpractical with this chessboard, so I would have to pick the frequencies that I would like the most based on the simplest ratio. So it's kind of really close to just intonation. It's not quite 5 limit just intonation, which is like a specific Renaissance tuning. Let's have a look. So the main part in here, and the most important bit of the circuit, is the Arduino that's doing all the calculation. It's running the code that converts what's happening in here in terms of voltage and digital signal into MIDI. So basically, underneath each individual square, there's this tiny module which contains a resistor, a tiny bit of universal circuit board, and a Hall sensor. That's the sensor that will detect the change in magnetic field, and that would send the signal to Arduino, and that would kind of convert that to MIDI. The main issue here, though, or the main issue I encountered when I was trying to design this, is that in order to detect each individual square separately, I would need 64 inputs in the Arduino, but it gets way less than that. So I use these chips, they're called shift registers, to squeeze in the 64 inputs or 64 streams of data into just these 3 cables there. Or actually it's just one cable basically. So the way this is done is one of these cables will send a signal for these little guys to read the state of each individual module. Each of these guys got 8 inputs, so that's why I have 8, because 8, by 8 is 64. So the signal gets sent, the shift registers will read the state, and then they will put the data in a series, in kind of a stream of ones and zeros that are in a particular order, and they will get synchronized with Arduino, and the Arduino will keep asking for the data, and the registers will shift it to Arduino. That's why they're called shift registers, in a single stream. And then using a bit of code, I can actually deconstruct this stream of data, a serial stream of data, into parallel inputs. So for me, it would be like having 64 individual inputs, except they're just in a particular order. So the only limiting factor in here is the speed, but it will read data, I think, like a couple thousand times a second. I think that they're capable of running on like 200 megahertz or something like that, something crazy. But I'm just running them on like 200 kilohertz, which is still really crazy. Basically, when you make a move, I would have to make a move in like 0.00001 whatever second in order for it not to work. So for even if I'm playing bullet chess, that's time control where you have only 1 minute to finish the game, I'm still not gonna be able to move the pieces fast enough for it not to work properly. Arduino is a microcontroller. It's this thing here. It's basically it's a really complicated voltage meter. That's what it is. That can run a piece of code. So basically, it will send a 5-volt signal, and it will measure on the input how much it's getting back. So if you have a digital input, it will only measure if it's receiving anything or not. So that will give you like a 0 or 1. 1 for, yeah, I got 5 volts, 0 for like, no, I got nothing. So that's how you can actually use these. So this is basically a switch controlled by magnets. So if I close the switch, that will mean I'll just shut the voltage down, so it will receive 0. And it will output 0 to computer, which is useful because I can work with that. If it's not shut down, it will output 5. volts. It will measure 5 volts, so it will output 1, which is, again, useful signal to have, because I can work with that as well. It can do other things. You can have analog inputs as well, so that would quantize the signal into, I think it's 16-bit quantizations. It's in the datasheet, you can read it. That will give you like a couple of different values you can get. So you can even record music on this one as you would on a music interface. It's only support, I think it will only support like 8-bit or 6-bit music, but it can do it. It can be done. Or you can output sound as well. You can say to the Arduino, let's just go output 5 volts, then do like 4.5, then do whatever in this particular time frame, and this way you can kind of construct the wave form of the sound. So you just plug a speaker in and you got a sound generated by computer. It can be done. It can do loads of things. It can do anything from like 3D printing, CNC, this thing, to like drones, basically anything. Because this, it's got like modules where you can like have added features to that, so you can receive Bluetooth, or you can hook it up with the internet, so you can control it from your phone as well. So you can just have an app, you press a button, it will switch something on for you, like heating or AC or whatever. So basically, when you design with Arduino, your creativity is the only limit.
Thanks to Jaroslav for this interview and for demonstrating some of the capabilities of this chessboard. It is truly a unique, one-of-a-kind creation, and I cannot wait to be there to document whatever it is you come up with next. The full dissertation is available in the links below, as well as Jaroslav's email, should you wish to get in touch with him to learn more about this project. Thanks again to Jaroslav, thank you all for watching, and until next time, take it easy.